So now that we understand what block ciphers are, let's see how to use them. And in particular, I'm going to use the concept of a PRF and a PRP, a pseudo-random function and a pseudo-random permutation, to explain how to use these block ciphers. So the first thing we'll do is we'll look at actually the wrong way to use a block cipher. And this is something called electronic codebook, which might be the first way you would think of using a block cipher, but it turns out to be very insecure. So let's see. So what would you do if you had a block cipher that operated on n-bit chunks, say, 128-bit chunks like AES, and now you wanted to encrypt a gigabyte of data? What would you do? Well, the natural thing to do is to take your plaintext and break it up into blocks, each one being 128 bits, and then encrypt each block separately. Okay, so each one of these is encrypted separately with the same key, of course. And so the ciphertext would be the same length as the plaintext, but this, unfortunately, is insecure. Why is this insecure? Well, the problem is if you have two blocks that are the same, for example, consider these two blocks here. Suppose M1 happens to equal M2, then in fact, well, because all we're doing is we're directly applying the block cipher to these blocks, then in fact, the corresponding ciphertext blocks will be the same too. So in fact, C1 will be equal to C2. So every time two blocks in your plaintext happen to be the same, the ciphertext will also be the same. So think of a voice conversation where encrypted traffic is being transmitted. Well, when there are periods of quiet in the voice conversation, basically zeros are being transmitted, and then an attacker will basically say, hey, every time I see this fixed set of patterns, this must be a quiet period in the phone conversation. This is an example where things might leak. A better example is to see this in pictures. Here's an example where we have this guy with very dark hair, and you can see that basically his silhouette is completely visible here, and I guess his collar and his shirts are completely visible because essentially the dark hair gets encrypted in exactly the same way. And so it's a good example of how ECB mode, electronic codebook, would leak information about the plaintext. Okay, so you never ever use this electronic codebook. We have to do something more sophisticated. So the first idea is to use something called cipher block chaining, CBC mode, cipher block chaining. And the idea here is as follows. So imagine, again, E is a secure PRP, so E is a secure pseudo-random permutation. Again, that's just another way of saying, it's an abstract way of saying that E is a block cipher. And the way we would encrypt is as follows. First of all, we choose an IV, and we'll talk about how to choose an IV in just a minute. And then, of course, we take our message and we break it into 128-bit blocks. So we break it into the blocks where each block is the size of the block cipher input. And then we start off as follows. We XOR the IV into the first message block, and then we encrypt the result. We encrypt the result, and that gives us our first ciphertext block. But now we also take our first ciphertext block and we use that to tweak the next block of plaintext. So now what actually gets encrypted by the PRP is the XOR of the plaintext block and the previous ciphertext block. Okay? And then we do the same thing again and again. The point is, if M0 happens to be equal to M2, C0 will not be equal to C2, right? They will not be equal because the ciphertext at this point is likely to be very different, actually will be very different, because the input to the PRP is very different in both cases, even though the plaintext blocks were the same, thanks to this extra XOR. You can see that, again, the PRP inputs are different, and as a result, the ciphertext blocks will be distinct. Okay, so the question is, how do we use these IVs? Well, it turns out that, in fact, if you're going to use the key just once, so in other words, in the block cipher mode, you're only going to use the key to encrypt a single message, multi-blocks, but a single message. Could be a gigabyte long message, but just one of them. Then, in fact, you don't have to use an IV at all. In other words, you could set the IV to 0, which means that really this whole part doesn't really exist. Okay, so M0 gets encrypted directly as is. And again, this works if the key is only used to encrypt one message, even if the message is quite long. Now, if you want to use the key to encrypt multiple messages, and the technical term for this is chosen plaintext security. Again, I would encourage you to take the crypto course if you want to understand this better. But if you're going to use the key to encrypt multiple messages, then in fact the best thing to do is to choose a fresh random IV for every message you want to encrypt. Okay, the IV is chosen fully at random from the plaintext space of the block cipher. But in fact, it turns out you can also use unique IVs if you wanted to. So for example, you could just use a counter. But then if you're going to use a counter, you have to do something more. In particular, you have to do one more step of encryption where you would actually take this counter and you would encrypt it one more time using the PRP before you actually use it. And the reason you want to do that is because when you encrypt a counter, because the block cipher itself is implementing a pseudo-random permutation, remember it's indistinguishable from a random permutation, well, what that means is we're encrypting a unique value. The output, therefore, will just be random, because a random permutation, or think of it as a random function output applied to unique values just produces random independent values. And as a result, this IV prime basically will be a random value for every different message. Okay, so it's very important to do this extra encryption step. So in fact, this IV prime will be different for every message. So why would we want to implement the IV as a counter as opposed to a random IV? Well, in some cases, both sides might already know what a counter is. For example, in the SSL protocol assumes the underlying network layer ensures in-order delivery, which means that the fifth packet sent by the sender is also going to be the fifth packet received by the receiver. So if they implement a packet counter, in other words, for every packet, increment the counter by 1 and use that counter value as a nonce, then there's really no reason to send the nonce over to the other side, because the other side already knows the packet number. They're generated in sync, the other side knows the packet number, and as a result, the other side can already decrypt without explicitly being told what the packet counter is. So by using counters as unique IVs, you might actually reduce network traffic because you don't have to send it explicitly. However, in protocols like IP that don't guarantee in-order delivery, in fact, the encrypted version of IP is called IPsec. There, the nonces have to be explicitly embedded in the packet because packets are delivered out of order, and so it's not clear that what number packet that was when it was sent from the sender. So there are some cases where a counter can save network traffic, and there are some cases where it can't. But again, I want to emphasize the best thing to do is to choose a fresh random IV. But I wanted to mention that there are tricks that you could do to reduce the amount of network traffic if there's already an implicit nonce between the sender and receiver. And here's just an example of CBC mode with a unique IV rather than a random IV. As I said, the one thing that's important to do is also encrypt this IV before you actually start using it. So you see this extra encryption that takes place before we start using the IV to actually do encryption. Okay, and of course this part, the IV then, the nonce, can either be transmitted as part of the ciphertext or not, depending on whether it's explicit or implicit. Okay, sometimes, by the way, this is called nonce-based encryption because we're not encrypting using random data, we're only encrypting using a nonce that's unique for every message. And again, I wrote down the specific requirement here. If you fix the key, the nonce has to be unique for every message. Of course, once you change the key, it's fine to reuse the same old nonce. Okay, and of course, if you look at CBC encryption in pictures, you see now you just get garbage, and the attacker can't figure out anything about the plaintext from the ciphertext. Okay, the second way to use a PRP for encryption is called counter mode. And this counter mode has some benefits over CBC. In particular, you notice if you look at the CBC picture, you notice that CBC is very sequential. In other words, the encryption of block M2 cannot be done until the encryption of block M1 is finished. Which means that if you have a parallel machine, if you have a machine, say, with multiple processors, it's kind of stuck. You know, you have one processor doing CBC encryption, but even though there might be multiple processors available for encryption, they cannot be used in parallel because CBC is inherently sequential. The benefit of counter mode is that, in fact, it is a parallel mode of encryption. You notice that every block here can be encrypted independently of the other. The way it works is as follows. We start with a random IV, and then what we do is basically we're going to encrypt the IV, this IV, and then we're going to encrypt the IV plus 1. Here, I'll use a different color. We're going to encrypt the IV, we're going to encrypt the IV plus 1, the IV plus 2, up to the IV plus L, where L is the number of blocks in the message. And then we're going to literally use these set of encrypted IVs as a one-time pad. And we're going to XOR this one-time pad with a message, and lo and behold, we get our ciphertext. Okay, so that's basically what's called counter mode. The benefit of counter mode is that these now encryptions, you can see the block cipher now can be run independent from one block to another. So if I have 5 AES engines, I can use all 5 AES engines to basically encrypt 5 message blocks at a time. So I gain a speed up of almost a factor of 5. Okay, and again here I described a mode where the IV needs to be random. There's similarly a mode where the IV can be a nonce, but I won't describe that here. The last thing I wanted to do is write down the performance numbers of the various block ciphers, and it's kind of interesting to compare them to stream ciphers. You can see stream ciphers are way faster than the corresponding block ciphers. Of course, the point is in the stream cipher, this has to be a one-time key, whereas a block cipher can be made secure, as if you use an appropriate mode, as we just discussed. I'll say can be secure for multiple messages. Can be secure for multi-use. But of course, that comes at a price where things are a little slower. I should mention this is on a 2.2 gigahertz machine, so it's kind of interesting that these encryption rates, the stream cipher encryption works almost at gigabit rates. Okay, the last thing I wanted to do before the end of this segment is end with a very important warning. And you cannot believe how often people don't heed this warning and make mistakes. The thing to remember is that everything we talked about is only about eavesdropping security. In other words, all we cared about was making sure that an eavesdropper who listens on the line cannot tell anything about plaintext from the ciphertext that he sees. But in most applications, in fact, an attacker can do much more. An attacker can actually tamper with traffic in the network and try to change things and see how the decryptor reacts to those changes. And very often, if all you do is CBC or counter mode encryption, it's going to be insecure against an active attacker, and an active attacker can actually decrypt ciphertexts by looking at how the decryptor reacts to different ciphertexts given to this decryptor. We might even do a homework project on this just to make sure that you understand how significant this danger is. So the bottom line is, even though we talked about CBC and counter modes, they should not be used by themselves. They always need to be used in conjunction with what's called a message integrity mechanism, something that provides security against tampering as well, and we're going to talk about message integrity in the next segment. Okay, but I do want to make sure you understand that these modes are not secure by themselves. We have to augment them with something to make them secure.